Hi, Leo.
Hi Aaron. So we're here live on Mount Etna. Hi everybody at home. And we're here to introduce the project ARCHES.
Right, it's an experiment series. We've been waiting a long time for this, so we planned to do this in 2020, but Corona. So here we are in 2022, finally on the volcano Etna, 2,700 meters above sea level.
And as you can see, or as you can probably see a little bit, the area is really impressive. It looks a little bit like the moon, Aaron. Could that be a reason why we're here?
Yes, it's a moon analog mission, which means we simulate an experiment on the moon. Of course, there are things we can't simulate. For example, on the moon there's no air. On the moon there's
Is there gravity? How about gravity? Yes,
yeah.
Exactly.
So we try and get the lessons that we can out of this. And maybe we can talk
Luckily, we're joined by the project leader, Armin Wedler, from the Institute of Robotics and Mechatronics. Armin, if you can just squeeze in here between us.
Okay.
And
I will do.
I just hold your microphone in front of you, and maybe you can just tell us what are we doing here? Why are we here?
Yeah, hello, Leo and Aaron. So that's the ARCHES project finally. So it's a 5-year campaign. We have been acquired in a project funded from the Helmholtz Association, and we are testing our technology we've developed in DLR, but also in cooperation with ESA, together to get higher technology readiness level, but also to explore operational scenarios, scientific data acquisition. So we have set up an analog lunar mission campaign here with 3 different parts in it. So geological sample acquisition, geological sample bring back or collection, bring back, soil acquisition. We have in situ instruments like a laser breakdown spectroscope, and we try to simulate a full mission with scenarios of a scientific team which is down in Catania.
So you already mentioned technology. I think the most spectacular technology, at least from the outside, are in fact robots, in fact rovers, right? They look a little bit like the Mars rover. Can you tell us a little bit about them?
Absolutely. I mean, we have 4 or 5 different rovers here, so there are 5 different robotic assets here. We have 3 wheel-based rovers, 1 from ESA, 2 from our Institute Robotic and Mechatronics Center. We have a Scout rover, which have wax wheels, but we also have an autonomous drone. So the technology we are developing in the Robotic and Mechatronics Institute, but also with the partners together, is mainly robotic technology. And here we have these different assets which are in this heterogenic manner. They're completing the functionalities since they are different. We have one with an arm, one with a scientific camera, and another one with
so quite a complex mission. Different robots doing different jobs.
Yes, absolutely.
But you also have different partners. You already mentioned the partners. Could you quickly tell us who are the partners again?
The partners of the initial ARCHES project is not only including this space analog mission which we see here, that's also including a deep sea exploration with robots, and there are mainly the partners Geomar and Alfred Wegener Institute involved, which are here now as guests, so the demo mission of them has already taken place. And here we have the KIT, the Karlsruhe Institute of Technology, but we also have the European Space Agency here, with some operational scenarios and tests, and with also the astronaut Thomas Reiter today.
Yeah, the astronaut is going to do some ESA tests, right?
He's operating an ESA robot. Exactly.
Excellent. Yeah, I think Aaron is going to tell us a little bit more about that later.
We'll hear from also, hopefully, Thomas, the leader of the ESA lab that's doing it. Currently, they're doing some tests with an astronaut, Thomas Reiter, but maybe when they're finished, then they can talk to us a bit about that.
Okay.
So
thanks very much, Armin.
Yeah. So one question reminds. So why does it have to be Etna on ARCHES? I mean, obviously it looks very impressive, but is there a real scientific reason behind it as well?
Yeah, there are a lot of research ongoing. There's also some studies on what different analog sites exist in the world, and as you can say, that there are different areas where different geological features are, where different scientific instruments can be probed. Vulcan in general have the soil parameters which are very likely to be used in robotic exploration. So we want to have new fresh earth, and we have that here. So we have fresh ash, we have outcrop of the volcan, which is very much expected as to be found on the planetary surface of Mars and Moon. So here we have also geological features like fumaroles and like mineralogical aspects are, let's say, having made us choose Etna. We had beforehand of the campaign, we had scouted different regions and different things.
Okay, great.
Yeah, it's interesting you say that, because I never really realized how much of a difference it makes until we brought our rover here. You know, our whole auto navigation, which we tuned for asphalt, basically,
Yes.
does not work here.
Yeah.
The wheels are slipping. You know, we have to do it completely again.
Absolutely. I mean, this is also something like I really much appreciated with all this different aspects. And I think it's important not only to do lab tests. It's important to make field campaigns.
Yes.
It's important to bring the things out. And another aspect is also this human aspect, let's say, because in this campaign we don't have, let's say, only technology validation. We have also scientists in one room with operational guys, maybe even connected from further outside.
Right.
And they all have different viewpoints on the system, on the way how things work. So bring that together is also like bringing humans together, which may speak different languages. So that's another psychology aspect, let's say.
It's good that you mentioned the human aspect, actually, and you already mentioned the real world, because we are obviously, I mean, we always say that with ARCHES we're getting one step closer to the moon, but we also have terrestrial applications with ARCHES, and I think we're going to look at one of them, and one of the things that, because there's always technology transfer happening at the Institute of Robotics and Mechatronics, and one of the projects that we're looking at, and one of the, we have a video prepared. And
Cool.
Armin is also the project leader of a project called AHEAD, where we work together with the World Food Organization. So I think we're going to have a quick look at the video now. Thank you very much, Armin. Thank you very much.
Great. Okay.
Hello, my name is Armin Widler, and I'm the head of the planetary exploration team in our Robotic and Mechatronics Center.
Hello, my name is Kyriakos Kouparis. I am the head of Frontier Innovations at the World Food Program Innovation Accelerator.
There's an initiative of DLR and humanitarian organizations. Part of World Food Program, there are several others NGOs, and we are looking for how technology we develop within the aim for being used for space, being applied to use terrestrial challenges of our society, which might also be very important.
The SHERP vehicle is currently being used in very difficult environments where food delivery is quite challenging. So the underlying problem is how can we deliver food without necessitating or putting drivers at risk.
From the approach of operating robotic assets on planetary surface in far distance, we have this challenge that we have to operate rovers and drive them with all the challenges of latency, of complexity in communication losses and that reasons. And so we see a lot of overlap in the challenges of teleoperating remotely planetary rovers and similar the shared vehicles in, for example, the use case region of South Sudan, where we try to envision this shared teleoperation.
Okay. Hi, Marcus.
Hi.
Good to have you
Hello.
here. So this is your drone.
Yes, that's the idea actually. It's a hexacopter which we fully from scratch developed at DLR.
Okay. Yeah, Mathilde, is it in the image? Can we see it? Okay, maybe we bring it a bit closer. Okay, so it's a hexacopter. That means 6 blades. And what is running on this drone? What does it do?
So it does a lot of stuff like on the system itself. So for instance, it can navigate just by itself. We don't need any GPS
like
on there.
autonomous flying. Okay.
Exactly. So instead of just flying manually, what you might want to do like with one of the drones you have at home, we can do that as well with the system, but we mainly just want to press on the button and then the drone does what it is supposed to do.
Okay, and these I see these cameras here. If I tilt it up a bit, maybe it can be seen.
You can also show on the camera if you want.
Yeah, okay, go for it.
Yeah.
You can show it to the... Great. So, and there is some processing, some computer stuff going on in there. Is it machine learning or is it, how does it interpret its environment?
Yeah, so maybe we start actually with the front. So we have these 4 cameras actually, which you see on the top there, right?
Okay.
So like one there, one there, one there, and one there.
Okay.
And we're actually combining the images there together, so we get stereo pairs. And then we can also see depth with it. It's like very similar what your eyes are doing as well. So we can actually see how far objects are away. And these ones, they are getting them processed on ADEA itself actually to get a depth map as well. And this information we are fusing then with an IMU, like inertial measurement units, like acceleration, gyroscope measurements.
So that knows basically in which direction it's accelerating, which way is down.
Exactly.
Okay.
It's kind of actually like your inner ear. So what we're doing is we're combining these camera images with the IMU information, and it's like what your brain does as well. You get like the eye, like what you see exactly, and also what your inner ear does. And with that, ADEA knows where it is. Because the problem when you're like on Mars or somewhere on the moon, you don't have GPS, so we cannot use
Because that was my next question. Why do you need a drone like that on a mission like that? Why is it important? What's the problem?
The specific skill for ADEA is actually that it can help you to scout very fast. So for instance, let's say we would be on a mission right now on Mars. Before you actually want to rove there with your rover, which can be very time consuming and can actually be also very dangerous. If you think about the Spirit mission, it actually got stuck there in sand. You first would like to explore, is there something interesting? Is it worth it to actually send the entire team there? And that's for what we have ADEA. We actually just fly over the very difficult terrain. We're also much faster, and then we can map the environment, and then we can see, is it really worth it to go there?
Well, I have a question. No, on like the moon and Mars, obviously gravity is very different. So how does it affect a drone?
So gravity would affect it. So even right now, actually up on Etna here, we had to...
we're 2,700 meters.
Exactly,
right?
and then where you actually are also on the planet, you have to change some of the parameters, but it's fine, like ADEA can do it. What's a little bit more of a problem here when you're on Etna is actually the air density. It's much thinner.
Oh, the air density, and also we have some problems, you might even be able to see it at home, that we have a lot of wind here.
Exactly, so it's very, very windy currently. We have like air speeds here currently of like roughly 35 to 40 meters per second. So that's very, very fast.
That's about as fast as a speeding car. On a 35 meters a second is like 80 kilometers a second?
Kind of when you
or even more.
We have to calculate it right now. But it's pretty fast,
we'll get
basically.
Back to you on that one.
Exactly. So I mean, usually what you would fly is like somewhere like 10 meters per second. So we're like at least 3 or 4 times too much.
Okay. And you mentioned the air density, but on the moon there is no air.
That's true.
So what are you going to do?
That's a big problem, right? So we also thought about this one when we designed ADEA. And what we did here is actually that we have like a two-step, modular approach here. So we have the inner part here, which we call the stack, which has all of the computational hardware actually. I can also lift it maybe a little bit. I'm not sure if you can see in the camera, but maybe I can show it like that. So there's all of the computational hardware in there. It's kind of the brain of ADEA. And you have the outside, which is the frame, which is the propulsion system. And depending on which mission we are, we can exchange this one. So for instance, if we're like in the lab right now, we would use a different frame, which has maybe smaller propellers because we don't need them so big, right? And the same idea right now is if you're on the moon, for instance, you don't need propellers anymore. There's no air, yeah? So for instance, we would then attach some thrusters, CO2 thrusters or something like that.
What is this?
And with this one, you could actually like generate lift again.
Okay.
Yeah, so it's just something like thrusters,
Little
or maybe
rockets.
like exactly.
Little, is it little, yes, exactly.
Kind
Is it
of like
little
that.
rockets? Is it like
Similar like that basically, and then you could fly again as well.
Okay.
Same thing, for instance, with the stack. If you would like to see something else instead of like just the images, we can have different sensors on there, and then we change the stack, but keeping the frame.
Okay, thanks Marcus for the introduction of ARDEA. Now ARDEA is going to work together with the LRUs,
Yes.
lightweight robot units, and on the LRUs there are some arms, there are some cameras,
Yes.
and I think we've got someone who's going to tell us what the LRU2 is going to do. Is that right?
So we have Heinz Wilhelm Huber here, who's going to introduce us to the
Yeah. Let's do
lift
logistics.
experiment. We just let Marcus
Thanks, guys.
leave. Thank you very much.
So
So yeah, there's different scientific experiments as we heard, and one of them is LIPS experiment. So what does LIPS stand for? What does it do?
LIPS, thank you for inviting me here. It's a great place. LIPS stands for Laser-Induced Breakdown Spectroscopy,
Yep.
which is a spectroscopic technique to analyze elements. And we are particularly interested in the elements which we find on let's say, Mars or on Phobos or on the Moon, and in the stones, whatever is there. Yeah. And so the technique works in rather straightforward. You have a small laser which emits strong laser pulses focused onto the stone or the sample, and basically the sample ablates or evaporates in a way, and all the atoms are in this so-called plasma, and the plasma emits light. All the elements which are in the stone are also in this plasma, in this little plasma, and we have a spectrometer to analyze this light emission, and each element which is in this plasma has a typical fingerprint emission, which we can then analyze, and afterwards we know which elements are in the plasma, and then we know which elements of course are in the stone, which we have investigated, and that's basically the technique.
And what do you hope to find? So considering we would go on, say, the dark side of the moon, or we consider we're going to talk later about that, we're going to go on Phobos, on one of the Mars
Yeah.
moons, what would you like to find?
Well, the interest is manifold actually. Once we know which elements are in this stone, let it be on Mars or on Phobos or on the Moon, it depends on the specific questions, but then we know, or we can learn about the history of the planet or the Moon, how it evolved, with how it was created and so on, because in certain stones and so on, under certain circumstances we find certain atoms and others are not there. For example, if we find a lot of hydrogen, we find a lot of hydrogen, that would be a sign of maybe there was water, or maybe there is water. Yeah, so it's a maybe, we don't know precisely, but it's a hint towards water, and of course, as you know, water is always the signature of life, so hydrogen is a very interesting element in this sense.
Okay. And what is most interesting for you personally about this campaign, this Etna campaign?
Well, about this campaign, the most interesting part is really that we learn under circumstances as close as possible to a real mission. So to do the remote operation, to command, to learn how we interact with the rover, what the rover can do for us, and how we feed back our information into the planning of the rover pathway, let's say. So this all together, that's the most important thing for us.
And why can't you do that in a laboratory, for example, just put a bunch of stones there and drive around
Well,
there?
we can all do this, of course, in the laboratory, and we can do it with more time and so on. But there's one piece of experience which we cannot get in the laboratory, and that is the setting of a real mission. You know, in the lab, you come in the morning, you go in the evening. You have everything perfectly set, the climate works and so on, heating, everything is perfect. Here we have rough conditions, we may experience complications with communication between the test site here on the top of the mountain and the base camp where the whole control room is. So all this we can experience here, and that's something we cannot learn in the lab. So we are very close to a real mission.
Okay, thank
Right.
you.
Thanks very much.
Thank
that was
you very much
insightful.
for explaining. Yeah.
Yeah, thank you.
And good luck with everything, of course.
Thank
right?
you very much. Thank
and
you.
Please enjoy your stay.
Yes.
Yeah, thank you. Bye.
So we have another guest lined up.
Hi, Emmanuel.
Hi, Emmanuel Staudinger. We now talked about the LIPS experiment, but there's another experiment called the LOFA experiment. So what is that all about?
So the LOFA experiment is actually a proof of concept demonstration of a radio telescope and the automatic deployment of the radio telescope itself. So the radio astronomers, they are interested in observing low radio frequencies which are very low. With that they can have a look at what's called the dark ages of the universe. So that's a span of the universe they want to investigate further. The issue with that is you cannot really observe those low frequencies very well on Earth.
Why is that?
Why? Yeah.
Well, simply you have a lot of background interference, so man-made from power lines whatsoever, and also the Earth's ionosphere blocks radio signals, for example, below 10 megahertz. And so they have the idea actually to go to the far side of the moon and deploy such an array on the far side of the moon.
Okay,
and there
because
you-
the far side of the moon is the side that never sees the Earth.
Exactly. And there you are perfectly shadowed from everything we generate, and you have a very pristine look into the universe. To achieve that, you need a couple of technologies which we developed in the framework of ARCHES. So, for example, we use a modular payload box design, where we have, for example, power boxes which provide energy. We have then the actual LOFA boxes, which include the radio receivers, which also include a particular radio navigation system from our side to localize them pretty well. Then you need all the autonomous navigation and manipulation capabilities of a rover, because a rover shall essentially pick those boxes from a lander deployed in the field in a certain configuration. Once they are deployed, you want to know precisely where they are. So the box position is it's very important to operate the array later on. For that, we also have a development from our side. It's a radio system where we can achieve that.
Okay,
So we can
but what do you, so because it sounds really technical to me and really exciting, but what is it that you personally hope to find? So you use all this amazing technology, but provided everything goes well, provided you can use the dark side of the moon, what do you hope to find?
Well, for me, so I'm not a radio astronomer, so I'm as an engineer. My main interest is to provide the technologies and the robust technologies for the astronomers to achieve that. And if we're able to do that, then the astronomers have a tool to really observe that part, or let's say that that age of the universe which cannot be observed so far. The fact that's a huge gain for them.
So it would be like a huge gain in knowledge for humankind, really,
Exactly,
right? If we see into
absolutely.
places that we've never seen into.
Absolutely.
That sounds really amazing. That sounds really exciting.
Right.
Thank you ever so much, Emmanuel.
Yeah, thanks very much. The rovers have to get to that place, basically. They're going to automatically deploy these, autonomously deploy the base stations for the telescope.
Exactly. Yeah.
Right. And for that, they need to know where they are. So we have the elusive Martin Schuster.
Yeah, and obviously as you can tell, it's a live experiment going on. So everybody's going backwards and forwards. It's all very exciting. But there he comes.
Yeah,
and
so
I
tell us who
think
you are.
Martin, without you, Martin Schuster from the Institute of Robotics and Mechatronics, and without you, the LRUs wouldn't find anything. Is that correct? Because you're responsible for navigation.
Yes, I'm responsible for navigation, so for the robots to know where they are, where the other robots are, and what the environment looks like, so to build a map of the environment.
And why is that so crucial in a mission like that?
So that is crucial because to reach certain target locations that scientists give for the robots, they need to know where they are to be able to travel there. And they need to know their surroundings so they can avoid obstacles and reach their destinations. And also to build a model of the environment that then humans can inspect later on. And as we are having here now multi-robot teams with different systems, it's also important that the robots share this information with each other and also know where their teammates are.
So they're effectively communicating with each other even though they're not the same kind of robot.
Yes, exactly. They are communicating, and they are communicating not only their own poses, but also parts of their environment model to share that. And also if they see, for example, certain landmarks, they communicate that as well so they can relocalize there, so they know they are back, for example, when they see the lander again.
Okay, what does localization mean? How, what is going on there? So how do they find where they are?
So in comparison to Earth, so here, for example, we humans, when we want to know where we are, we just open our smartphone, pull up Google Maps, and then via GPS, it tells us where we are. But that requires satellites in the orbit. And for moons and other planets, we usually don't have that number of satellites that would be needed for such a system. So that's why the robots need to rely on the onboard sensors. These are usually cameras, inertial measurement units, so they are measuring basically how far they move, and also based on wheel odometry. And fusing that sensor information, they localize themselves. But the issue is, with that local information, if they travel far, they get an error in their estimation. So they are less sure where they are when they travel further away. Basically like humans do when they don't have anything to reference themselves.
And this could also be used, I guess, on Earth. I mean, this is obviously an amazing step for space travel, but this could also be used on Earth.
Yes, so these technologies, both of this local navigation and relocalizing, so referencing back to when you've seen something to know that you're back, basically, that is also very useful technology for robots on Earth, for example, in search and rescue missions, where robots also often need to operate without good satellite coverage. So for example, when they need to enter a cave or a partially destroyed building, like we had now in Fukushima, then the robots need to rely on their onboard systems. And that is very similar to what they need to do in space.
And that's something that the Institute of Robotics and Mechatronics also specializes in, actually. Right?
Yes, yeah. And actually we are also transferring that knowledge from space technologies down to Earth. For example, in the project ahead, where we use it for humanitarian help, the same technologies.
Yeah. You can hear there's really a lot of stuff going on in the background. Thank you ever so much, Martin. We also we talked a little bit about applications on Earth. We talked about applications on space, and we're talking about this Analogue mission. But there is in fact a real mission coming up, and Marcus Graverstein of the Institute of Robotics and Mechatronics is going to tell us about one.
Hi, Lioba.
Hey, Marcus. Thank you for joining us. So.
Yeah, what is MMX?
What is MMX? What are you planning to do? There's a real mission coming up.
Yeah, so MMX is a Japanese mission, and this Japanese mission is supposed to bring samples back from the Martian system. Not in particular from the Martian system, from the Martian moon Phobos, which is a very interesting place to visit, because there we have very likely materials that are maybe even from outside of the universe, and materials that are from the Martian sphere, which basically means we can search for the origins of life, etc., on this Martian moon. And within this mission, we are contributing together with our partner CNES, Rover.
CNES is the Japanese.
No, it's the French.
Oh, the French agency.
It's the French agency, and together we are building a rover that is supposed to drive on the surface and do in situ science there on the surface.
Mm-hmm. And as far as I know, nobody has been on Phobos before, right? So this would be a first-time attempt to go there?
Yes, never before there was a successful landing on Phobos. So the Italians tried, they failed. So a couple of missions tried to land there. So the Japanese will be the first to land on the Phobos, but we are even earlier than because we are a rover on board of the spacecraft, and we're just thrown down onto the surface from the spacecraft, because the purpose of our contribution to the JAXA mission is that we should basically scout the surface of Phobos to find out what are interesting regions to visit, where is it good to land, where's a few stones only, where's a soft ground, etc.
Okay,
Wait, and when is this happening?
The launch will be in 2024. The rover has to be delivered next year, around this time, and the samples from the JAXA mission will be brought back around 2029, which would be the first material from the Martian system returning to Earth.
Okay.
Exciting.
What is actually special about Phobos as opposed to Mars? Why not just go to Mars?
That's basically this bifold origin of material on the Phobos surface. So one assumes that Phobos is not a split up part of Mars or something like that. Many people assume that it is basically something that came from the outside of the universe, was captured by Mars, and is flying around Mars. And on Phobos you can see blue areas, which is basically the original Phobos material, and red areas. And in the red areas, it is very likely material from Mars. So Mars erupted material, and the gravity on Phobos basically has brought this material on the ground of Phobos. So you find both materials, you can take samples of both and investigate whether there's an origin of life. Is this origin of life on Mars? Is it from the outer universe, etc., etc.?
Okay, thank you. So again, there will be a rover deployed, and we have quite a few rovers here, as we mentioned, and one of them, Aaron, is working really closely with. So thank you very much, Marcus. And now, Aaron, I'm really curious, what's going on with that Interact rover? of
Sure,
yours?
the Interact
Thank
rover.
you.
So the Interact rover is, I don't know if you can see it, but currently they're training an astronaut on it, because tomorrow an astronaut is going to operate it, not from the ISS, from Catania. So it's a very robust rover. It's got some manipulation arm, or one manipulation arm, and one arm that can look around with a camera. And it's actually not
Sorry,
designed.
a manipulation arm means it can grab stuff,
It means
can
it
move
grabs
stuff, right?
So what we've most recently used it for is grabbing rock samples. And that was the case in a 2019 mission, which I'll talk to you about. Just describing the rover itself, it's the biggest rover that we have here. And it's not really, our interest is not the hardware, so how do you build a rover for to go to Mars or to go to space. The tires, for example, the tires are just normal rubber tires, and you'd never send that to space. What is interesting,
Why not?
Because, I mean, first off, on the moon, for example, the temperature is really low. So these rubber...
So they would deflate completely, or and get brittle?
They would get brittle, so they would just break. I mean, it's just a bad idea on all accounts. And of course, if they're inflated, then if there's any pressure, they'll just explode.
Yes.
So explode into lots of tiny little pieces, maybe. What we're interested in is how the human interacts with it. So we had a mission in 2019 where there was Luca Parmitano from the on the ISS. Luca Parmitano is actually a native of Catania, I think, or Sicily, and he operated it from the ISS. This time we weren't on Etna; we were just in the Netherlands. Boring.
In the ESA testing grounds, right?
In a hangar somewhere. But for the first time, there was a full degree of freedom. So that's not just in one or two directions, but in all directions. Teleoperation from orbit to ground. So that means that Luca on the space station was able to grasp rocks by inserting his hand into a force feedback device, grasp them, feel them.
And then it has like a pressure thing, right?
There's
that
a
you can,
gripper on the
like a
robots.
gripper with.
He was able to pick them up, feel gravity while being weightless, which is probably crazy, I don't know. And, really interact with the ground in a way that was not
Hence the
possible
name,
before.
I guess.
Yeah.
Hence the name. Excellent.
And this is the second part of the mission, where we're doing it in a more realistic setting rather than a hangar, an aircraft hangar, but the astronaut is on ground.
And we already mentioned that you have gripper. Some of the one of the LRUs has an actual hand being developed, which was developed by KT. So again, it's the heterogeneous, the large variety of the rover. Yes. A lot of different rovers doing a lot of different things. Speaking of different things, we're here from the Institute of Robotics and Mechatronics, where we also have lots of different things. Obviously, this is space. This is space research. We do space exploration, orbital exploration, but we also have a lot of stuff, a lot of knowledge transfer happening from space to Earth, but also actually not obviously from Earth technologies being fed back into space technologies. And I think as we talk to a lot of experts today, they're all, as you can tell, really busy going on with their experiments. we're going to end up by showing you a big overview of all the different areas of technologies in the Institute of Robotics and Mechatronics. So thank you very much, Aaron.
Before we do that, maybe I can try panning with that camera so people can see a bit more of the...
Yeah, oh God, yeah,
Yeah?
cool.
We've taped it down because, as you can hear, the wind is crazy here.
Yes, even the laptop had to be taped down because we were worried that it might fly away. So the wind is really, really challenging.
Yeah, I just want to see if we can see the Scout Rover behind. Yeah.
Let's give you, as a final thing, let's try and give you a 360-degree view of the... We're here at base camp.
Is it working?
Of the base camp.
Okay.
It's obviously shaking a bit now, but...
Can we see the Scout Rover? Does it fit? Yeah, you can see the Scout Rover just between there, so you can see the wheels there. Unfortunately, they have another one. Yeah. Is it working? Yeah, maybe you can just see through there. There's a rover on the ground. It's not moving, unfortunately. And then here, this is the extent of the mission. There's a lot of people here. It's our demo day. And Leo, can I give you that? And then maybe they can get a view of the lander.
Okay, let me just give you a quick look around the corner. So there's the landing site. There's a lot of people here today. As Aaron said, we're having a big demonstration. The astronaut is here today. Lots of people. There's media interest in everything.
Yeah.
So with a beautiful view of Mount Etna behind you, I hope you can see it. We say bye from Etna and show you a big overview. We show you a big overview from the Institute of Robotics and Mechatronics. Thank you.